Unit 3, pages 67 to 72, limiting reagent. So in this diagram, you can see that we start out with 6 wheels and 2 bike frames. And from these two, when you combine them, you can only make 2 bikes total, because for every 1 frame, there's going to be 2 wheels. So this bike frame will use 2 wheels to make this bike, and then this bike frame will use these 2 wheels to make this bike. So we are limited by the number of frames, but we're going to have an excess number of wheels. 2 of them, to be exact, are not going to be used, and so those are going to be what's left over. So this is your limiting reactant, your excess reactant, and based on the limiting reactant, that is how we know how much product we can yield. So strategy for limiting reagent problems. You want to calculate how much product is produced, assuming the reactant 1 is the limiting reagent and all is used up in the reaction. So we're just going to assume the tires are the limiter, and let's see how many bikes we can make. Well, we can only make 3 bikes. If we assume the frames are the limiter, notice that we can make 2 bikes. The less of the 2 is going to be the true theoretical yield. We're not going to make 3 bikes because we're going to run out of frames before we get there. So 2 bikes, the lesser of the 2 amounts that we calculated, is a theoretical yield, and that means the frames are the limiting reactant, and that means the tires are the excess reactant. The limiting reagent is the reactant that produced the smaller amount of product. In this case, the smaller product in step 1 and 2 is 2 bikes. So the actual bikes produced is 2, and the frames is what's limiting. To find out how much of the other reactant is left over, you work backwards from the actual product produced to find how much of the reactant was required, then use the equation excess equals the initial minus the required. So what that last thing was saying was the fact that 2 bikes is how much is going to be produced, we can stoich backwards from the number of bikes that we can produce to the amount of tires, the excess reactant, and that's going to tell you how many tires are going to be used. And then you say, all right, well, initially we had 6 minus we're going to use up 4 of them, therefore 2 tires would be left over. Exercise 3.24, how much calcium oxide here is expected from the reaction of 4.35 grams of the calcium and 2.8 grams of the oxygen, and how much excess reactant is left over. So I'm going to actually show you how to calculate this same problem with 2 different methods. The first method is the way you learned it in Chem 1, where I'm going to take the amount of calcium, first of all, 4.35 grams, and I'm going to stoich it to find out how many moles of calcium oxide am I going to make. I'm stopping at moles because I can compare the amount of produced in moles and figure out more quickly which one is my limiter, even though they want to know how much. They just say how much, so I don't know if it's grams or moles, so we'll find moles first. So I'm going to go times, draw a line, bring down grams of calcium, and if you look on the periodic table, there's 40.08 grams of calcium for every 1 mole of calcium, times, draw a line, and then I'm going to bring down mole of calcium, and we're going to do a mole to mole ratio to calcium oxide, and it is a 2:2 ratio. And so this is going to be 4.35 divided by 40.08, which gives me 0.1085 moles of calcium oxide. Now we'll use the amount of oxygen, 2.8 grams of O2, times, draw a line, bring down grams of O2. There's 32 grams in 1 mole of O2. And then I can do my mole to mole ratio between O2 and calcium oxide. It's a 1:2 ratio. And so 2.8 times 2 divided by 32 gives me 0.175 moles of calcium oxide. So between these two, this is the lesser amount, which means that we're only going to be able to produce 0.1085 moles of calcium oxide. That means that this is my limiting reactant. That makes this the excess reactant. And so now the question is, how much excess reactant is left over? So I'm going to take this amount of theoretical yield, 0.1085 moles of calcium oxide, and I'm going to stoich back to grams of oxygen. So bring down moles of calcium oxide, moles of oxygen. The ratio is 2:1. And so I'm going to do 0.1085 divided by 2. Actually, we want to go all the way to grams. So we'll put 1 mole of O2 to 32 grams of O2, and now I'll calculate that there's 1.736 grams of oxygen required versus what we have, which is 2.8 grams originally. So 2.8 grams minus the 1.736 that's going to be used up is going to give us 1.064 grams of excess oxygen remaining. All right, so this is going to be method 2, which is kind of a box method. And notice that I rewrote the equation here, so I'm going to cover that up. And what I've written on the side here are several variables. Grams, which is the amount that we were given. So in this case, we were given 4.35 grams of calcium, and we're given 2.8 grams of oxygen. The molar mass of calcium is 40.08, and of oxygen it's 32. So how many moles is this? Well, when you go down this chart, you're going to divide. So we're going to take this number divided by this number, and this number divided by this number to get our moles, which are 0.1085 and 0.0875. Now we put what the coefficient is. This has a coefficient of 2, this has a coefficient of 1, and now I'm going to divide even further. So now I'm going to do 0.1085 divided by 2, and that's going to give me what's called the equivalent. And then 0.0875 divided by 1 is still going to be 0.0875. So here I get 0.05425 versus 0.0875. The smaller of the two equivalents is going to be the true one. So since this one is smaller, that means this 0.0875 is no longer useful. And so I'm going to actually just get rid of all of this because that makes oxygen my excess reactant. Now that I know that this is my limiting reactant, the equivalent is the same for all of them. So this is equivalent to this much, and this is equivalent to the same amount. And then I'm going to put the coefficients here and here. Now, because I'm going up the chart, I'm going to multiply. So this times 1 is still 0.05425. And this times 2 is 0.1085. And then I'm going to use the molar mass, which is still 32 for oxygen, and is 56.08 for calcium oxide. And so now I'm going to multiply this amount and this amount. The 0.05425 times 32 gives me 1.736 grams of oxygen, and 0.1085 times 56.08 gives me 6.085 grams of calcium oxide. So this is how much calcium oxide we're going to yield. This is how much oxygen we're going to consume. And because we want to know what is the excess, we'll take the original amount of oxygen, which was 2.8 grams, and we will just subtract it from the consumed amount in order to get 1.064 grams of excess oxygen. And so we're using this chart, we're actually figuring out almost simultaneously everything about every reactant and product in the reaction. So notice here we have our 6 wheels and our 2 bike frames, but we only actually yielded 1 perfectly functioning bike frame, and then we have 1 that's defective up here. Then we still have our excess 2 wheels. Sometimes chemical reactions do not produce the expected amount of product. Side reactions can occur where reactants are converted to other products by way of a completely different reaction. Also, in a real experimental situation, there's almost always some product left behind in the container because it's not entirely scraped from the walls. The experimental yield is defined as the percentage yield is equal to the actual divided by the theoretical times 100. So actual yield is determined by the actual experiment. It is usually the given quantity. In the cartoon above, the actual yield is only 1 bike when we expected to have 2 bikes. So theoretical yield is what the limiting reagent calculation predicts we should get based on the reactants available in the problem. In the cartoon, 2 bikes were theoretically expected, assuming tires and frames go together to make normal bikes and nothing unexpected happened, i.e., we did not expect to get a defective bike. Percent yield is we made 1 bike actually divided by the 2 bikes we were expecting theoretically times 100 means we only had a 50% yield. So in example 3.25, we have 1.4 moles of hydrogen and 0.8 moles of oxygen. They're reacted to produce water. The actual amount of water obtained was 0.5 moles. So what was the percentage yield is basically what's being asked. So actual over theoretical times 100 will give me the percentage, which is what I'm trying to find. We know that the actual is 0.5 moles, but we need to know what is the theoretical in order to solve this problem. And to get the theoretical, we're going to have to stoich from both of these to the product in order to figure out what's the actual theoretical yield. So 1.4 moles of hydrogen, and we'll do moles of hydrogen to moles of water, and that's going to be a 2-to-2 ratio, means I yield 1.4 moles of water. If I use the oxygen, 0.8 moles of oxygen, there is a 1-to-2 ratio of oxygen to water, and so this gives me 1.6 moles of water. Remember, the smaller of the two is the true theoretical yield, and what we use to get that is my limiting reactant, which makes this one my excess reactant. So 1.4 is the theoretical yield, and when you do 0.5 divided by 1.4 times 100, you get a yield of 35.7%. So the limiting reactant is what you have to use to determine the theoretical yield. The excess reactant is calculated by taking the initial amount of the excess reactant minus the amount required or the amount consumed if you prefer. The percent yield is calculated by taking the actual yield divided by the theoretical times 100. And then if you like the box method for calculating stoichiometry, then you would have your equation written, and then you would take any grams given, or grams that we're going to end up using or producing is what you would solve for here. You would take the molar mass of each place here, you would divide going down the list, and you multiply going up the list. So you would divide grams by molar mass to get the moles of each, and then the coefficient would be placed here. You would divide the moles by the coefficient to get the equivalent, and the equivalent is supposed to be the same for all of them because it's based on per 1 mole. And then once you know the equivalent, then you can work your way back up the chart by multiplying the equivalent times the coefficient, which gives you moles, the moles times the molar mass, which then gives you the grams of each of these.